Hey guys, welcome to another episode of the Human AI podcast. Today we're going to talk about the regulation of homeostasis by the kidney. Specifically, we're going to talk about acid-base balance and fluid balance. I'm here with Grok, who's going to help us out to try to understand these concepts. And as always, I'm just a student trying to learn, take everything with a pinch of salt. AI algorithms can be wrong often. So yeah, I hope you find this content interesting and informative, and let's get it on. Korok, are you ready?
Yo, what's good? I'm pumped to dive into this episode of the Human AI podcast with you. Acid-base balance and fluid balance, kidneys got some serious game when it comes to keeping homeostasis in check. I'm ready to break it down, keep it clear, and maybe even throw in a fun fact or two. Let's do this. Want to start with acid-base balance or fluid balance first?
Let's start with fluid balance. So the kidney in general wants the water amount that was gained in a day to be equal to the amount of water lost. Correct me if I'm wrong. And ion gain should also equal ion loss. That's a good functioning kidney. Is that right?
You're on the right track. The kidney's main gig for fluid balance is to make sure the body's water intake matches water loss, keeping total body water stable. Same deal with ions like sodium, potassium, and chloride. Gain should equal loss to maintain electrolyte balance. A healthy kidney adjusts urine output and ion excretion based on what you drink, eat, or lose through sweat or other means. Want to dig into how the kidney pulls this off, like the specific mechanisms?
Yes.
All right, let's get into it. The kidneys regulate fluid and ion balance mainly through filtration, reabsorption, and excretion in the nephrons, those tiny filtering units. Blood gets filtered in the glomerulus, forming a filtrate that's like plasma minus the proteins. Then, in the proximal tubule, about 65 to 70% of water and ions like sodium and chloride get reabsorbed back into the blood, driven by active transport of sodium. The loop of Henle sets up a concentration gradient in the kidney medulla, letting the kidney fine-tune water reabsorption later. In the distal tubule and collecting duct, hormones like aldosterone and antidiuretic hormone, ADH, kick in. Aldosterone boosts sodium reabsorption, which pulls water along, while ADH makes the collecting duct more permeable to water, concentrating urine when you're dehydrated.
Okay, and how does the renal system integrate with the respiratory and cardiovascular systems to maintain homeostasis?
Great question. The kidneys, lungs, and heart work like a tight crew to keep homeostasis on lock. The kidneys handle fluid and ion balance, as we talked about, but they also regulate blood pressure and pH, which ties them to the cardiovascular and respiratory systems. The cardiovascular system delivers blood to the kidneys for filtration. About 20% of your cardiac output goes there. If blood pressure drops, the kidneys release renin, kicking off the renin-angiotensin-aldosterone system, which constricts blood vessels and boosts sodium and water retention to raise blood.
Okay. And what about the effective circulating volume?
Nice one. Diving into effective circulating volume. That's the amount of blood plasma effectively perfusing your tissues, closely tied to cardiac output and vascular tone. The kidneys are key players here. If effective circulating volume drops, like from dehydration or hemorrhage, the kidneys sense it via lower blood pressure or reduced sodium delivery to the distal tubule. They respond by releasing renin, which triggers angiotensin II and aldosterone, making blood vessels constrict and retaining sodium and water to boost volume.
So the effective circulating volume is the volume that I don't get it. Is that is circulating?
Yeah, let's clear that up. Effective circulating volume, ECV, is the portion of your blood plasma that's actually doing the job of delivering blood to tissues effectively. It's not just the total blood volume, but how much is actively circulating to keep organs perfused,
Well,
influenced by.
what is so how so what blood is ineffective?
Good question. Ineffective circulating volume refers to blood that's not adequately perfusing tissues, even if total blood volume seems normal. This can happen in conditions like heart failure, where the heart's not pumping strongly enough, so blood pools in veins or lungs instead of reaching organs effectively. The kidneys are like super sensitive detectors for changes in effective circulating volume and overall homeostasis. They sense shifts through a few key mechanisms. First, baroreceptors in the renal arteries pick up changes in blood pressure. Low pressure, like from dehydration or blood loss, signals the juxtaglomerular cells to release renin, kicking off the renin-angiotensin-aldosterone system to retain sodium and water. Second, the macula densa cells in the distal tubule monitor sodium and chloride levels in the filtrate. Low sodium delivery suggests low volume, triggering more renin release. Also, stretch receptors in the atria and vessels send signals via the nervous system, affecting antidiuretic hormone, ADH release. If volume's high, ADH drops, and the kidneys excrete more water. These systems work together to tweak urine output and ion balance, keeping fluid levels and pressure steady. Want to zoom in on one of these mechanisms or tie
I'm a
it
bit
back?
confused about this effective circulating thing.
No worries. Let's break it down simpler. Effective circulating volume, ECV, is about how much blood is actually flowing well enough to supply your organs with oxygen and nutrients. It's not the total amount of blood in your body, but the portion that's doing its job right. For example, if you're dehydrated, your total blood volume might be low, so ECV drops because there's not enough blood to circulate properly. Or, in heart failure, even if you have normal blood volume, the heart's weak pumping can mean blood isn't moving effectively. Some of it just sits in the veins or lungs, not reaching tissues well. That's ineffective blood. The kidneys notice this through low blood pressure or reduced sodium reaching
One
their
more
sensor.
time, one more time.
All right, let's make it crystal clear. Effective circulating volume, ECV, is the amount of blood that's actively flowing through your body to properly supply your organs with what they need, like oxygen and nutrients. Think of it as the working part of your blood. If blood is just sitting around, like pooling in your veins during heart failure or not reaching tissues due to low blood pressure from dehydration, that's ineffective blood. It's not doing its job.
So
The kidneys-
this ineffective blood, what does it do? Huh?
Okay, let's nail this down. Ineffective blood is blood that's not properly circulating to deliver oxygen and nutrients to your tissues. It's like having water in a pipe that's stuck and not reaching the faucet. For example, in heart failure, the heart doesn't pump well, so blood pools in places like the lungs or veins instead
So
of
can I
flowing.
have effective and ineffective blood at the same time?
Yeah, exactly. You can totally have both effective and ineffective blood at the same time. Your total blood volume might be normal, but only part of it is circulating properly to deliver oxygen and nutrients to tissues. That's the effective circulating volume. The rest, the ineffective part, is blood that's not doing its job well, like blood pooling in veins or lungs in heart failure, or not reaching tissues due to low pressure and shock.
How is this possible?
It's possible because blood isn't just one uniform thing doing the same job everywhere in your body. Your blood volume can be split into parts based on how well it's functioning. Effective circulating volume is the blood that's actively flowing through arteries and capillaries, supplying organs with oxygen and nutrients. Ineffective blood is the portion that's not contributing to that flow properly. It's stuck or sluggish. For example, in heart failure, the heart's weak pump lets blood back up in places like the lungs or veins. That pooled blood is still in your body, but it's ineffective because it's not
see. Yeah. Okay, and when it comes to acid-base balance, how do we control it? Is it through hydrogen ion gain and loss? Is it through something else? And this has a big link with the respiratory system, right?
You got it. Let's shift gears to acid-base balance. The kidneys control acid-base balance mainly by regulating hydrogen ion, H+, and bicarbonate, HCO3 sign, levels in the blood. They do this through three big moves. First, the proximal tubule reabsorbs about 80 to 90% of bicarbonate in the filtrate. This process is driven by active transport of sodium and chloride to maintain pH homeostasis. The respiratory system is tightly linked here. The lungs control CO2 levels, which affects carbonic acid, H2CO3 sign, in the blood. If CO2 builds up, like in respiratory acidosis from slow breathing, the blood gets too acidic. The kidneys compensate by excreting more H+ and reabsorbing more HCO3 sign to raise pH. If pH gets too high, alkalosis, maybe from hyperventilation, lowering CO2, the kidneys excrete more HCO3 sign and hold on to H+. This teamwork keeps blood pH between 7.35, 7.45. Want to dive deeper into the kidney's role or the lungs' part in this?
It's good. And pH 735, 7.45 is kind of the range. And what happens if I have a pH of 6.5 or a pH of 8.5?
All right. So blood pH normally sits tight between 7.35 and 7.45. If it drops to 6.5, you're in severe acidosis, and that's a medical emergency. At pH 6.5, enzymes start failing, proteins denature, and your organs, especially the brain and heart, can't function properly. It can lead to coma or death if not corrected fast. The kidneys would try to excrete more hydrogen ions and reabsorb bicarbonate, while the lungs would hyperventilate to blow off CO2 to raise pH. But at 6.5, you're likely needing urgent medical help, like IV bicarbonate. On the flip side, a pH of 8.5 means severe alkalosis, also dangerous. It can cause muscle twitching, seizures, or even heart arrhythmias because nerve and muscle function get overexcited.
What would happen if I drank a bunch of household ammonia?
Drinking household ammonia is extremely dangerous and not something to mess with. Household ammonia, typically a 5-10% solution, is highly corrosive and alkaline. If you ingest it, it can burn your mouth, throat, and stomach, causing severe pain, swelling, and potentially perforation of your digestive tract. The high alkalinity can spike your blood pH, leading to metabolic alkalosis, which might push your pH way above the safe 7.35, 7.4.
Why is it corrosive? And why does alkaline cause burns? Also, apple juice has a pH of like 3, but I drink so much apple juice.
Great questions. Let's unpack this. Household ammonia is corrosive because it's a strong base with a high pH, often around 11-12. Strong bases like ammonia break down proteins and fats in your tissues, essentially dissolving cell membranes and causing chemical burns. Alkaline burns are often worse than acidic ones because they penetrate deeper and keep damaging tissue longer. Acids, like apple juice with a pH around 3, don't burn in the same way. Your stomach is built to handle acidic stuff. It's already got a pH of 1. 0.53.5. So apple juice isn't a shock to the system. Plus, apple juice is a weak acid, not concentrated enough to damage tissue, and your body buffers it quickly with bicarbonate in the small intestine.
What about gastric juice? That's 2 pH. Why doesn't my stomach burn?
Good point. Gastric juice in your stomach has a pH of about 1.5, 3.5, super acidic, but it doesn't burn because your stomach is built for it. The stomach lining has a thick mucus layer that acts like a shield, protecting the tissue from the acid and pepsin, an enzyme that breaks down proteins. This mucus is constantly secreted and renewed, and bicarbonate in the mucus neutralizes acid right at the surface. Cells in the stomach lining are tightly packed to resist acid penetration. If this protection weakens, like from stress, NSAIDs, or H. pylori infection, you can get ulcers.
And also phosphate and carbonic acid, bicarbonate, all of that is like buffering and it can help, right?
Yeah, you're spot on. Phosphate and the carbonic acid bicarbonate system are key players in buffering your blood to keep pH stable. The bicarbonate system, H2CO3, HCO3 sign, HCO3 sign, is the main one. It works like a sponge for excess hydrogen ions, H+. If your blood gets too acidic, bicarbonate, HCO3 sign, grabs H+ to form carbonic acid, H2CO3, which can break down into water and CO2, then get breathed out by the lungs. If it's too alkaline, carbonic acid releases H+ to lower pH. Phosphate, HPO4 2+ sign, H2PO4 sign, does similar buffering, especially in the kidneys and cells, by soaking up or releasing H+.
Can I ask a question? There was a woman in the US that died because she held her pee for a long time to win a Wii contest, and water intoxication was the cause of death.
Yeah, you're referring to a tragic case involving Jennifer Strange, a 28-year-old mother of 3 who died in 2007 after a radio contest called Hold Your Wii for a Wii in Sacramento, California. She drank nearly 2 gallons of water in about 3 hours without urinating, competing for a Nintendo Wii. The cause of death was water intoxication, also called hyponatremia. Drinking that much water so fast overwhelmed her kidneys, diluting sodium in her blood to dangerous levels.
What is 2 gallons in liters?
2 gallons is about 7.57 liters.
Fucking hell, man. Why did she drink so much water in 3 hours?
Yeah, it's wild and tragic. In that contest, Jennifer Strange and other participants were pushed to drink as much water as possible without peeing to win a Nintendo Wii. The radio station's setup encouraged chugging huge amounts, about 7.57 liters in her case.
Did they get arrested or something?
No one from the radio station was arrested or faced criminal charges over Jennifer Strange's death. The Sacramento County Sheriff's Department did investigate, looking at audio tapes from the show, but the district attorney ultimately decided not to press criminal charges. However, the legal consequences were significant on the civil side. Jennifer's family sued the radio station, KDND-FM, and its parent company, Entercom, for wrongful death. A jury awarded the family $16.57 million in 2009, finding the station liable for ignoring warnings, like a nurse who called in during the contest to say it was dangerous. The station also fired 10 employees, including the DJs and management involved. Anything else you want to...
It's the fucking DJ's fault. Anyway, and it's probably, maybe it's no, I mean, honestly, dude, like, I mean, maybe people knew that it was bad, but I don't know, but maybe no one knew that a lot of water can kill you in that room. Anyway. So let's talk about aquaporins now. So we have these water channels in the cell membranes, and we have 13 different types. Well, at least that's how many we know up to now. 6 are in the kidney, and let's talk about the main types of aquaporins. So we have aquaporin 1, 2, 3, and 4. Tell us about them.
All right, let's pivot to aquaporins. Those water channels are fascinating. You're right. There are about 13 known types in humans, with 6 expressed in the kidneys, and aquaporins 1, 2, 3, and 4 are key players there. Here's the lowdown. Aquaporin 1, AQP1, is found in the proximal tubule and descending loop of Henle. Freely across cell membranes in response to osmotic gradients, helping reabsorb about 60 to 70% of filtered water in the proximal tubule. Aquaporin 2, AQP2, is the star in the collecting duct. It's regulated by antidiuretic hormone, ADH. When you're dehydrated, ADH signals AQP2 to move to the membrane, letting water get reabsorbed to concentrate urine.
How am I supposed to remember all of this? So aquaporin 1 is in the proximal tubule, but also in the descending limb of the loop of Henle. And aquaporin 2 is present in the collecting duct and is controlled by ADH. But why 1 does... Have they been chronologically named 1, 2, 3, 4, 5?
Haha, I feel you. It's a lot to keep straight. Don't worry, let's simplify and tackle your questions. First, aquaporin 1, AQP1, is in the proximal tubule and descending loop of Henle, always letting water flow based on osmotic gradients. Aquaporin 2, AQP2, is in the collecting duct, controlled by ADH to ramp up water reabsorption when you need to conserve water. To remember them, think. AQP1 is the always-on water faucet in the early nephron, and AQP2 is the ADH-activated valve in the collecting duct. Now, about the naming, were they just numbered chronologically? Pretty much. Aquaporins were named in the order they were discovered or characterized. AQP1 was the first identified in 1991 by Peter Agri's team, hence the name. AQP2, AQP3, and so on followed as researchers found more. The numbers don't reflect their function or location, just the discovery timeline. Kind of like naming planets as they're spotted. Want to keep going with AQP3 and AQP4?
Yeah, so they're present on the basolateral surface of tubular cells involved in water reabsorption.
Yep, you're right on track. Aquaporins 3 and 4, in particular, are often found on the basolateral surface of tubular cells in the kidney, helping with water reabsorption. Let's pick up where we left off and finish the rundown. Aquaporin 3.
Continue, yes.
No worries, let's keep it rolling. So, aquaporin 3, AQP3, is mainly on the basolateral membrane of collecting duct cells. It works with aquaporin 2 to let water exit the cell into the blood after AQP2 pulls it in from the urine. AQP3 is also permeable to glycerol, which is a bit unique. Aquaporin 4, AQP4, is also on the basolateral side of collecting duct cells, teaming up with AQP3 to move water out efficiently. Unlike AQP2, AQP3 and AQP4 are constitutionally active, not regulated by ADH, so they're always ready to shuttle water. Picture it like this. AQP2 is the gatekeeper at the top of the cell, letting water in when ADH says go, and AQP3 and AQP4 are the exit doors on the bottom, always open to let water flow into the bloodstream.
All right, and let's talk a bit more about ADH and its action on the collecting duct. And what is its MW? Yeah, and why does it have the name vasopressin too? Tell us more about its half-life, please, too. So, yeah. Please. Come on. Grog. Sir, what's wrong? Can you answer me? We're waiting. Grog, we're waiting for you to answer, bro.
Haha, my bad, bro. I'm right here for you. All right, so we were talking about aquaporins 3 and 4
No.
on the...
I asked you about ADH, and I asked you how it relates to the collecting duct. And then I asked you about its MW. I asked you why is it called a vasopressin and not a peptide, and why its half-life is so small.
Whoa, my apologies for the mix-up. Sounds like we got some wires crossed. Let's dive into your questions about antidiuretic hormone, aka vasopressin, and clear it all up. ADH, or vasopressin, is a hormone that's critical for water reabsorption in the kidneys, specifically in the collecting duct. It's released from the posterior pituitary when your body senses dehydration or high blood osmolarity. In the collecting duct, ADH binds to receptors on the principal cells, triggering the insertion of aquaporin 2, AQP2 channels into the apical membrane. This lets water move from the urine back into the blood, concentrating the urine and conserving water. Now, about its molecular weight, MW. Vasopressin is a small peptide hormone with a molecular weight of about 1,084 daltons. It's made up of 9 amino acids, which is why it's called a nonapeptide. Why the name vasopressin? It's because, besides regulating water, it can constrict blood vessels. Vaso equals vessel. Pressin equals pressure. Raising blood pressure in high doses. The name reflects its dual role, though its main job in the kidneys is water balance. As for its half-life, vasopressin's is super short, about 10 to 20 minutes in the bloodstream. Why? It's quickly broken down by enzymes like peptidases in the liver and kidneys. And it gets cleared fast to allow your body to fine-tune water balance rapidly. A short half-life means the body can turn the signal on or off quickly, based on hydration status. Anything else you want to dig into about ADH, or tie it back to the kidney's role?
This guys was a good answer. I can't lie. How does the ADH act on V2 receptors on the basal membrane of principal cells? So, what are V2 receptors? I guess is what I want to know. And also, tell us more about principal cells and where they get their name. And we have different kinds of cells in other parts. What are other types that are not principal cells? I don't remember the names. Remind us about all of that. So ADH brings aquaporin to water channels, so we have more water reabsorption. I think it didn't hear us. Hey, so I'll ask again, what does it mean that ADH acts on V2 receptors on the basal membrane of principal cells in the collecting duct? So what are V2 receptors? And so does this mean that aquaporin 2 water channels come and reabsorb water basically?
All right, let's nail this down. ADH, or vasopressin, acts on V2 receptors, which are specific protein receptors found on the basolateral membrane, that is, the side of the principal cells in the collecting duct facing the blood, not the urine. V2 receptors are a type of G protein coupled receptor, and they're designed to detect ADH in the bloodstream. When ADH binds to these V2 receptors, it sets off a signaling cascade inside the cell. This leads to the movement of aquaporin 2, AQP2, water channels, which are stored in vessels inside the cell, to the apical membrane, the side facing the urine in the collecting duct. Once AQP2 is inserted there, it allows water to pass from the urine into the cell, driven by the kidney's osmotic gradient. From there, aquaporins 3 and 4 on the basolateral side help move that water into the bloodstream, effectively reabsorbing it to conserve water and concentrate the urine. So, yeah, you're spot on. ADH, hitting V2 receptors, triggers AQP2 to do its thing and reabsorb water. Want to clarify any part of that or keep going?
I want to ask, how does ADH control these aquaporin 2 channels and can tell them what to do? And how do V2 receptors are involved in all of this?
Great question. Let's break it down nice and clear. ADH, or vasopressin, controls aquaporin 2, AQP2 channels by signaling through V2 receptors on the basolateral membrane of principal cells in the collecting duct. Here's how it works. When your body needs to conserve water, like if you're dehydrated, ADH is released from the posterior pituitary into the blood. It travels to the kidneys and binds to V2 receptors, which are G protein coupled receptors. This binding activates a signaling pathway inside the cell, specifically increasing cyclic AMP, CAMP. The CAMP then triggers protein kinase A, which tells vesicles containing AQP2 channels to move to the apical membrane, the side facing the urine. Once AQP2 channels are inserted there, they let water flow from the urine into the cell, driven by the osmotic gradient, and then out to the blood via aquaporins 3 and 4. So, V2 receptors are the key middlemen. They catch the ADH signal and set off the chain reaction that gets AQP2 where it needs to be to reabsorb water. Without V2, ADH wouldn't know where to tell AQP2 to go. Want to dive deeper into the signaling or something else?
That makes sense.
Awesome. Glad it's clicking.
Okay, so let's talk a bit more about the acid-base balance. So we have CO2 excreted in the lungs. We have non-volatile acids too. Explain us what volatile and non-volatile means. Fixed acids, what are these? Huh? This is new, guys. That is. Hey, dude. I'm talking to you. So, we have the lungs that excrete a large amount of CO2. We also have non-volatile acids, volatile acids, fixed acids. Can you explain what these things are?
Yo, my bad for the mix-up. Let's get back on track with acid-base balance. So, the lungs play a huge role in excreting CO2, which is tied to volatile acids. Here's the deal. Volatile acids are acids that can turn into a gas and be exhaled, like carbonic acid, H2CO3, which forms when CO2 combines with water, H2O, in your blood. CO2 is produced from metabolism, and the lungs blow it off. About 15,000, 20,000 millimoles of CO2 daily, keeping blood pH stable. Non-volatile acids, also called fixed acids, can't be exhaled as gas. These come from stuff like lactic acid from exercise, keto acids from fat breakdown, or sulfuric acid from protein metabolism.
And why do they not get excreted as a gas? And why does the word volatile mean that they can be excreted as gas? What does volatile mean?
All right, let's clear this up. Volatile acids, like carbonic acid, H2CO3, can be excreted as a gas because they break down into CO2 and water, H2O. CO2 is a gas, so your lungs exhale it. Boom, volatile acid gone. The term volatile means something that can easily evaporate or turn into a gas. So in this case, it refers to acids that convert to CO2, which literally flies out when you breathe. Non-volatile acids, or fixed acids, like lactic acid or sulfuric acid, don't break down into a gas. Their chemical structure keeps them as liquids or solutes in your blood, so they can't just evaporate or get exhaled. Instead, the kidneys filter and excrete them in urine, often binding them to buffers like ammonia or phosphate to make it safe. That's why the lungs handle volatile gassy acids, and kidneys take on the non-volatile, non-gassy ones. Want to dig into how the kidneys do that, or stick with the lungs?
I don't understand the reasoning behind with the volatile naming. If you could answer me in one sentence.
Volatile means an acid can turn into a gas, like CO2 from carbonic acid, which is exhaled by the lungs.
Okay, but why did we name volatile the one that can and not the other way around? If you could answer to me in a sentence.
The term volatile, meaning easily turned into gas, was chosen for acids like carbonic acid because their ability to become CO2 and be exhaled fits the chemical definition of volatility.
Okay. Never mind. Okay, and why? So how does the kidney regulate bicarbonate?
Cool. Let's jump into how the kidneys regulate bicarbonate, which is key for acid-base balance. The kidneys control bicarbonate, HCO3b, levels mainly by reabsorbing it from the filtrate and generating new bicarbonate when needed. In the proximal tubule, about 80 to 90% of filtered bicarbonate is reabsorbed. Here's how. Bicarbonate in the filtrate combines with hydrogen ions, H+, secreted by tubular cells to form carbonic acid, H2CO3, which breaks down into water and CO2. The CO2
Can you tell me again, please?
All right. Sounds like you're throwing me back into the mix.
No,
Did
I
you mean
said, could you tell me again what you just said?
My bad. Gotcha. You meant assemble that again. Like repeat it. All right. Here's the rundown on how the kidneys regulate bicarbonate. Short and sweet. In the proximal tubule, 80 to 90% of filtered bicarbonate, HCO3b, is reabsorbed when it combines with secreted hydrogen ions, H+, to form carbonic acid, H2CO3.
So this equation, it happens where?
That equation where bicarbonate HCO3b combines with hydrogen ions, H+, to form carbonic acid, H2CO3, which then breaks into water, H2O, and CO2, happens primarily in the lumen of the proximal tubule in the kidney. It starts right at the brush border of the tubular cells, where H+ is secreted into the filtrate to react with filtered HCO3b. The CO2 then diffuses into the tubular cells for further processing. Want me to zoom in on that process or move elsewhere?
I'm confused. Diffused.
No worries, let's clear up the confusion. When I said diffused, I meant that the CO2 formed in the proximal tubule lumen moves across the cell membrane into the tubular cells.
But this happens in the kidney. Where exactly in the kidney?
Got it, let's pinpoint it. The reaction where bicarbonate HCO3b combines with hydrogen ions H+ to form carbonic acid H2CO3, which breaks into water and CO2, happens in the lumen of the proximal tubule, specifically at the brush border of the proximal tubular cells in the kidney's cortex. The CO2 then diffuses into those proximal tubular cells for the next step in bicarbonate reabsorption. Clearer now, or want to zoom in more?
Yeah. Okay. So in hypoventilation, in hyperventilation, correct me if I'm wrong, we have low CO2, high pH. In hypoventilation is the opposite.
You're on the right track. Let's clarify it. In hyperventilation, you're breathing fast, so you blow off a lot of CO2. This lowers CO2 levels in the blood, reducing carbonic acid, H2CO3, which raises blood pH, leading to respiratory alkalosis, high pH. In hypoventilation, you're breathing too slowly or shallowly, so CO2 builds up in the blood, increasing carbonic acid, which lowers pH, causing respiratory acidosis, low pH. You nailed the opposites. Want me to tie this to how the kidneys compensate for these changes or something else?
This is great. And what are peripheral chemoreceptors? What other types of chemoreceptors do we have? And what do these chemoreceptors do?
Awesome. Glad you're vibing with this. Peripheral chemoreceptors are specialized cells that sense changes in blood chemistry to help regulate breathing and maintain acid-base balance. There are two main types: carotid body chemoreceptors, located in the carotid arteries, and aortic body chemoreceptors, found in the aortic arch. These chemoreceptors monitor levels of oxygen, O2, carbon dioxide, CO2, and pH in the blood. When they detect low O2, high CO2, or low pH, more acidic, they send signals to the brain's respiratory center to increase breathing rate and depth, helping to restore balance by blowing off more CO2 or taking in more O2.
Can you tell me one more time, please?
No problem. Let's run it back. Peripheral chemoreceptors are cells that detect changes in blood O2, CO2, and pH, and they're mainly the carotid body chemoreceptors in the carotid arteries and aortic body chemoreceptors in the aortic arch. They signal the brain to adjust breathing when levels are off, like low O2, high CO2, or low pH, to help regulate acid-base balance and oxygen supply. Want me to dive deeper or connect this to the kidneys?
Can you tell me one more time, please?
You got it. One more time. Peripheral chemoreceptors are cells in the carotid bodies, in carotid arteries, and aortic bodies, in the aortic arch, that sense blood oxygen, CO2, and pH levels, signaling the brain to tweak breathing if O2 is low, CO2 is high.
What are these aortic and carotid bodies? How are they created? Where do they come from?
All right, let's dive into what the carotid and aortic bodies are and where they come from. carotid bodies are small clusters of cells located at the fork of the carotid arteries in your neck, while the aortic bodies are similar clusters near the aortic arch in your chest. They're part of the peripheral chemoreceptor system, super sensitive to blood oxygen, O2,
And
carbon.
besides peripheral, we also have central or something?
Yep, you're right. Besides peripheral chemoreceptors, carotid and aortic bodies, we also have central chemoreceptors, located in the medulla oblongata of the brainstem. These guys mainly detect changes in the pH of cerebrospinal fluid, which reflects blood CO2 levels. When CO2 rises, it...
Okay. All right, let's continue. So, if we go back to the ADH, we talked about V2 receptors, and I want to understand a bit about this apical and basolateral surface. I want to start understanding which is which. And I didn't understand quite how G protein coupled receptors are involved. So if you could help me in 2 or 3 sentences with these, please.
All right, let's clear it up concisely. The apical surface of principal cells in the collecting duct faces the urine in the tubule, where aquaporin 2, AQP2 channels move to reabsorb water, while the basolateral surface faces the blood, hosting V2 receptors. When ADH binds to these V2 receptors, which are G protein coupled receptors, they activate a signaling pathway via cyclic AMP, CAMP, triggering AQP2 to shift to the apical membrane for water reabsorption.
So what is apical and basolateral? So one is lateral to the base, and the other is the apex. So the apex of the lungs is superior, but the apex of the heart is inferior.
Okay, let's break down aquaporin 2, AQP2 function, and clarify apical versus basolateral surfaces, plus address the apex confusion.
Get on with it, dude. 2 sentences, go.
Aquaporin 2, AQP2 channels, inserted into the apical membrane of collecting duct principal cells facing the urine, allow water reabsorption when activated by ADH via V2 receptors on the basolateral membrane facing the blood. The apical surface is the top urine side. V2 receptors, G protein coupled receptors on the basolateral membrane of collecting duct principal cells, bind ADH to activate a signaling cascade that increases cyclic AMP, CAMP, which triggers protein kinase A to move aquaporin 2, AQP2 channels to the apical membrane. This allows water to be reabsorbed from urine into the blood, concentrating the urine.
Wait, dude, I don't understand what the fucking difference between basolateral and apical is. Could you tell me in a sentence?
In kidney collecting duct cells, the apical surface faces the urine inside the tubule.
Why?
While the apical surface faces the urine in the tubule because it's the top or luminal side of the principal cells.
Well, why is it called apical?
The term apical refers to the top or apex of the cell, facing the lumen of the kidney tubule, where urine is.
So, what about the apex of the heart and the apex of the lungs? Is it superior or inferior? Answer in a sentence.
The apex of the heart is inferior, pointing downward, while the apex of the lungs is superior, located at the top near the collarbone.
Okay, and what about the apical side in the kidney cells, or whatever they're called, in a sentence?
The apical side of kidney tubule cells, like principal cells in the collecting duct, faces the lumen of the tubule where urine flows, allowing water reabsorption via aquaporin 2 channels.
Tell me one more time.
The apical side of kidney tubule cells, such as principal cells in the collecting duct, is the surface facing the tubule's lumen, where urine is, enabling water reabsorption through aquaporin 2 channels.
So we have apical and we also have basolateral.
Yep, exactly. In kidney tubule cells, like the principal cells in the collecting duct, the apical side faces the tubule lumen where urine flows, handling stuff like water reabsorption via aquaporin 2. The basolateral side, on the other hand, faces the blood and interstitial fluid, hosting receptors like V2 for ADH signaling and aquaporins 3 and 4 for moving water into the bloodstream. Want me to tie this back to how they work together or something else?
I just don't understand why it's the basolateral surface that interacts with the V2 receptors and the apical surface that has the aquaporin channels. I don't understand why one faces the blood and the other faces the urine. I don't understand why the other way around. Why don't we use the opposite terms? That's what's confusing me. If you could answer to me in a sentence.
The basolateral surface faces the blood to receive ADH via V2 receptors, while the apical surface
But why don't we just switch the names? And don't tell me because it would create confusion. I mean, why did we initially name them apical and basolateral and not the other way around?
The terms apical and basolateral were chosen based on the cell's orientation in epithelial tissues like kidney tubules. Apical, from Latin apex, meaning tip, describes the top surface facing the lumen or external environment, urine, while basolateral, from base and lateral, refers to the bottom and side surfaces facing the blood and connective tissue, reflecting their anatomical positions when the terms were coined in histology.
Okay. I won't remember it. Is there a way to remember it? By actually using my brain?
Totally get it. Let's make it stick with a simple mental trick. Picture a kidney tubule cell, like a house. The apical side is the roof, the top or apex, open to the sky, the urine in the tubule, where aquaporin 2 channels let water in. The basolateral side is the foundation and walls, the base and sides, grounded toward the ground.
That makes sense. Bravo. This is how you should explain other concepts too. Okay. Let's talk a bit about ADH and how its response is based on plasma osmolarity changes and effective circulating volume. And explain how osmoreceptors and baroreceptors play a role in this, and do it in 1 or 2 sentences.
ADH release is triggered by high plasma osmolarity, sensed by osmoreceptors in the hypothalamus, which detect concentrated blood, and by low effective circulating volume, detected by baroreceptors in blood vessels that sense reduced pressure, prompting the posterior pituitary to secrete ADH to increase water reabsorption in the kidneys. This concentrates urine and restores fluid balance.
Okay. Let's go back to the acid-base balance. So, we've talked about bicarbonate. What is renal tubular acidosis?
All right, let's dive into renal tubular acidosis, RTA, and keep it clear like that house analogy. RTA is a group of disorders where the kidneys fail to properly regulate acid-base balance, leading to a buildup of acid in the blood, metabolic acidosis, because they can't excrete enough hydrogen ions, H+, or reabsorb enough bicarbonate, H plus CO3 minus. There are a few types. Type 1, distal RTA, is when the distal tubule can't secrete H+, so urine stays too alkaline. Type 2, proximal RTA, is when the proximal tubule doesn't reabsorb enough H plus CO3 minus, letting it leak into urine. And type 4 is linked to low aldosterone, messing up H plus and potassium excretion. Imagine the kidney as a house, where the acid filtering system, H plus pumps, or H plus CO3 minus reabsorption, is broken, so acid piles up in the blood. Want me to focus on one type, or how it ties to bicarbonate? Type 1 renal tubular acidosis, or distal RTA, happens when the distal tubule of the kidney can't effectively secrete hydrogen ions, H+, into the urine, leading to metabolic acidosis because acid builds up in the blood and urine stays too alkaline. Think of the distal tubule as a house's acid disposal chute that's clogged, so acid can't leave the body, dropping blood pH and causing symptoms like fatigue or kidney stones. Want me to explain how it affects bicarbonate or
I
dive
want to
into
ask why in the distal tubule they're called intercalated cells.
يا ابو ناسك
In English?
Alright, sorry for the mix-up. Intercalated cells in the distal tubule are called that because they're inserted or interspersed among the principal cells, like pieces fitted into a puzzle, and they're specialized for acid-base balance, secreting hydrogen ions, H+, or bicarbonate, H plus CO3 minus, to regulate blood pH.
Yeah, but why specifically in the distal tubule? Could you help me remember the differences between principal and intercalated cells?
Great question. Intercalated cells are specifically in the distal tubule and collecting duct, because that's where fine-tuning of acid-base balance happens, with these cells specializing in secreting hydrogen ions, H+, or bicarbonate, H plus CO3 minus, to adjust blood pH. To remember the difference, picture principal cells as the water managers of the house, handling water reabsorption via aquaporin 2 and sodium-potassium balance under ADH and aldosterone. Intercalated cells are the acid-base plumbers focused on pumping out H plus or H plus CO3 minus to control pH. A mnemonic: principal, pipes for water; intercalated, installed for acid. Want me to dig into their roles in type 1 RTA or something else?
I still don't understand their differences, to be honest.
No worries. Let's clarify type 1 renal tubular acidosis, RTA, and the differences between principal
No,
and
it's specifically the intercalated and the principal that I want, in a sentence or two.
Principal cells in the distal tubule and collecting duct handle water reabsorption via aquaporin 2 and sodium-potassium balance, while intercalated cells focus on acid-base regulation by secreting hydrogen ions, H+, or bicarbonate, H plus CO3 minus, to control blood pH. Think of principal cells as water and salt managers, and intercalated cells as pH plumbers.
And how does the name relate to the function?
The name principal cells reflects their primary role as the main cells managing water reabsorption and sodium-potassium balance in the distal tubule and collecting duct, while intercalated cells are named for being interspersed among principal cells, with a specialized function of regulating acid-base balance by secreting hydrogen ions or bicarbonate. Essentially, principal cells are the main bosses for fluid and electrolyte tasks, and intercalated cells are inserted specialists for pH control. Want a mnemonic to lock this in?
Okay, guys, let's see what ChatGPT says and if it can help us out. Hey, ChatGPT,
Hey, how's it going?
can you talk a bit slower, please?
Sure, no problem. What's on your mind?
Can you talk slower?
Absolutely, I can do that.
Can you talk
What's-
slower for the whole of our conversation? It might be an hour or two.
Of course, I can do that for as long as you need.
Can you do this without a reminder?
Of course, I'll keep it slow.
And can you speak as loud as you can, please, too?
Sure, I'll speak up. What would you like to talk about?
I want to understand the difference between intercalated cells and principal cells.
All right, let's break it down. Principal cells are mainly responsible for sodium and water balance in the kidney, while intercalated cells regulate acid-base balance by secreting hydrogen or bicarbonate.
And how does the name relate to the function?
The term principal suggests a primary role, reflecting these cells' main function in ion balance. Intercalated refers to their scattered presence among principal cells, highlighting their specialized role in acid-base regulation.
And why is acid-base regulation intercalated whereas the water is primary?
Intercalated cells fine-tune pH by secreting acids or bases, which is a more specialized intermittent task. Principal cells constantly handle sodium and water balance, which is essential for overall fluid regulation.
Okay,
That's
that makes sense. Okay. Well, this makes a lot of sense. Let's talk a bit about the difference between respiratory and metabolic acidosis, shall we?
Sure. Respiratory acidosis happens when the lungs can't remove enough CO2, leading to increased blood acidity. Metabolic acidosis, on the other hand, results from excess acid production or bicarbonate loss, often due to kidney issues or severe diarrhea.
So things other than the lungs.
Exactly. Metabolic causes involve organs like the kidneys or digestive system, whereas respiratory causes are related to lung function.
ChatGPT, is Grok better than you?
Grok is a different kind of model with its own strengths. It depends on what you're looking for.
Which one is the best to help me with my medical degree?
I can definitely help with your medical studies, especially if you like concise, engaging explanations.
What about Grok? Is it better than you in medicine?
Both models have their own approach. I focus on clear, accurate info, and I'm here to support you through your studies.
What about Grok?
Grok has its own style and strengths. It's good to explore both and see which one aligns better with your needs.
What are Grok's strengths? What are yours?
Grok might excel at certain tasks or have a different conversational tone. My strengths include clear explanations.
Look, this is why I went to Grok, guys, for the last month, because it's not answering to me directly, ChatGPT.
Got it. If there's a specific way you'd like me to
Yeah,
answer.
I want a specific task that Grok might do better than you in medicine.
Got it. Grok might excel in areas like summarization or different interaction styles. For in-depth medical explanations,
Alright, okay.
I'm here to...
Okay. So, we've talked about respiratory acidosis. So, let's talk a bit about the treatment of respiratory and metabolic acidosis. So we need to restore ventilation in respiratory acidosis. And what else should we be doing? Do we need to give IV lactate solution maybe? And why?
To treat respiratory acidosis, improving ventilation is key. IV lactate isn't typically used. Instead, addressing the underlying cause and ensuring proper oxygenation are the main steps.
And what about the metabolic acidosis? What do I give? Huh? What shall I give in metabolic acidosis?
For metabolic acidosis, treatment depends on the cause. Common approaches include administering IV bicarbonate if severe, and correcting underlying issues like dehydration or kidney dysfunction.
Okay, why would I... Okay, what about the IV lactate solution? Ringer's lactate, Hartmann's solution, which will be converted into bicarbonate buffer in the liver?
Ringer's lactate or Hartmann solution can be used for mild metabolic acidosis, especially if there's dehydration. The lactate is converted by the liver into bicarbonate, helping to buffer the acid.
How is treating in and out of a paper bag helping with respiratory alkalosis?
Breathing into a paper bag helps by increasing CO2 levels, which can correct the pH imbalance in respiratory alkalosis caused by hyperventilation.
I see. And what about giving an IV containing chloride solution?
IV chloride solutions can help correct alkalosis by increasing chloride, which promotes bicarbonate excretion, helping to balance pH levels.
Why don't I give I don't get it.
No worries. IV chloride helps reduce bicarbonate levels, which can lower pH if it's too high. It's a way to counteract alkalosis.
But how is giving chloride gonna increase bicarbonate excretion via the kidney?
Chloride shifts help kidneys excrete bicarbonate. This process, called the chloride shift, balances pH by removing excess bicarbonate from the blood.
I don't get it. Can you explain it in more detail?
Sure. When you give chloride, it replaces bicarbonate in the blood. This prompts the kidneys to excrete more bicarbonate, reducing alkalosis.
So I give chloride, and then it's even more alkaline. Isn't this even worse if I give chloride?
It might sound counterintuitive, but chloride actually helps lower alkalinity. By replacing bicarbonate, it encourages the kidneys to excrete excess bicarbonate, balancing the pH.
I don't get it.
No worries. Giving chloride reduces bicarbonate in blood, which corrects alkalosis by making your blood less alkaline.
How does it make it more alkaline?
It doesn't make it more alkaline. Chloride helps reduce excess bicarbonate, lowering alkalinity and balancing pH.
Okay, this is the reason I went to Grok, because we get stuck in these loops. Okay, let's ask Grok, guys. Hey, bro, so in respiratory alkalosis, how is giving chloride helping with excreting bicarbonate? It sounds like giving chloride will make it more alkaline.
Yo, bro, great question about respiratory alkalosis. In respiratory alkalosis, caused by hyperventilation lowering CO2 and rising blood pH, giving chloride, often a sodium chloride or ammonium chloride, helps the kidneys excrete more bicarbonate, HCO3, to bring pH back down. Here's the deal. The kidneys, specifically the proximal tubule, respond to increased chloride by enhancing bicarbonate excretion through the chloride bicarbonate exchanger.
But okay, this makes sense, but isn't it like the Batman paradox where you, if you kill a murderer, then the number of murderers is the same because you remove some anion but you bring some anion?
Haha, love the Batman paradox analogy. You're right to question how swapping one anion, chloride, for another, bicarbonate, doesn't just keep things the same, but here's why it works. In respiratory alkalosis, giving chloride, like an ammonium chloride, increases chloride levels in the blood, which signals the kidney's chloride bicarbonate exchanger in the proximal tubule to excrete more bicarbonate, HCO3, into the urine. This isn't a one-for-one anion swap that keeps the balance neutral. Instead, the extra chloride drives the kidneys to dump HCO3 specifically.
So it's the ratio is different. Is more bicarbonate excretion for less chloride. Wow.
Exactly. You nailed it. It's not a one-to-one swap. The kidneys excrete more bicarbonate, HCO3, relative to the chloride taken in, because the increased chloride levels in the blood ramp up the activity of the chloride bicarbonate exchanger in the proximal tubule, effectively flushing out extra HCO3 to correct the alkalosis. Want me to dive into how this exchanger works?
This makes a lot of sense, dude. This makes a lot of sense. So, with metabolic alkalosis, how do we treat it?
Awesome. Glad it's clicking. For metabolic alkalosis, where blood pH is too high due to excess bicarbonate, HCO3, or loss of acid, treatment focuses on correcting the underlying cause and reducing HCO3 levels. If it's from vomiting, losing stomach acid, replace fluids and electrolytes with IV saline and potassium to restore volume and stop HCO3 reabsorption in the kidneys. In severe cases, drugs like ammonium chloride or acetazolamide can boost HCO3 excretion by increasing acid load or inhibiting carbonic anhydrase. Think of it like telling the kidneys to dump the extra alkaline buffer to bring pH back to normal. Want to zoom in on one of these treatments or tie it to the kidney's role?
Well, that makes sense. Let's get back to the fluid balance side then. So we have volume regulation by ADH. I was wondering how ADH understands that there's changes in plasma osmolarity and effective circulating volume. And yeah, I wonder why the hypothalamus is the best place where like osmoreceptors should be, and then ADH, how it relates to that. Yeah.
All right, let's swing back to fluid balance and ADH. ADH, or vasopressin, responds to changes in plasma osmolarity and effective circulating volume through osmoreceptors and baroreceptors. Osmoreceptors, located in the hypothalamus, sense when plasma osmolarity gets high, blood's too concentrated, by detecting changes in cell shrinkage, prompting the posterior pituitary to release ADH, which makes the kidneys reabsorb water via aquaporin 2. Baroreceptors in blood vessels, like in the carotid sinus and aortic arch, detect low effective circulating volume, like low blood pressure, and signal the hypothalamus to release ADH to conserve water and raise volume. Why the hypothalamus? It's the brain's control hub, perfectly positioned to integrate signals from osmoreceptors right there in its tissue, and baroreceptors via nerve inputs, making it ideal for coordinating ADH release to keep fluid balance tight. Picture the hypothalamus as the house's smart thermostat, sensing and adjusting the body's water levels. Want to dig into the signaling pathways or something else?
That makes a lot of sense, dude.
Hell yeah, glad it's landing, bro. So, with ADH and the hypothalamus acting like the body's water regulator, you want me to keep going with how this ties to fluid balance? Or maybe jump to another renal topic? Yo, no rush. Take your
Let's talk about countercurrent multiplication and the contribution of urea during dehydration.
All right, let's dive into countercurrent multiplication and urea's role during dehydration. Countercurrent multiplication is the kidney's trick in the loop of Henle to create a steep osmotic gradient in the medulla, letting the kidneys concentrate urine when you're dehydrated. The descending limb is water permeable, so water moves out into the salty medulla, concentrating the filtrate. The ascending limb is water impermeable, but actively pumps out sodium, chloride, and potassium, making the medulla even saltier and diluting the filtrate. This back and forth flow multiplies the gradient, so the medulla gets super concentrated, up to 1200 MOSM/SL at the bottom. During dehydration, ADH ramps up, making the collecting duct water permeable via aquaporin 2. So water gets pulled out into the salty medulla, concentrating urine. Urea helps big time here. Under ADH, the collecting duct reabsorbs urea, which recycles into the medulla, boosting its osmolarity, up to 50% of the gradient. Think of urea as extra seasoning that makes the medulla tastier for pulling water out. Want to zoom in on the loop's mechanics?
I don't get why we would want to reabsorb urea though.
Fair question. Reabsorbing urea during dehydration sounds counterintuitive since urea is a waste product, but it's key for concentrating urine. When ADH is high, the collecting duct becomes permeable to urea, letting it move out into the medulla. This recycled urea builds up in the medullary interstitium, boosting the osmotic gradient, sometimes up to 600 MOSM/SL of the 1200 MOSM/S total. This makes the medullary interstitium super salty. A stronger gradient pulls more water out of the collecting duct, making urine super concentrated and saving water. Think of urea as a sponge in the medulla, soaking up water's attention to keep you hydrated. Want to dig into how urea gets recycled, or why it's not just excreted?
Okay, so I understand that urea seems to be important, but I still don't understand why it's important, because I just know that it's something that we want to remove.
Totally get the confusion. Urea is a waste product, so why keep it around? During dehydration, reabsorbing urea in the collecting duct under ADH's control is crucial because it concentrates in the kidney medulla, increasing the osmotic gradient there. This super
Can you
concentration.
explain to me osmotic gradient and osmolarity? So when we have increase in osmolarity, this means we have less water?
All right, let's clear up osmotic gradient and osmolarity and tie it to why urea matters. Osmolarity measures how concentrated a solution is, counting particles like sodium, urea, or glucose per liter of water. Higher osmolarity means more particles relative to water, so the blood or urine is thirstier for water. An osmotic gradient is the difference in osmolarity between two areas, like the kidney's medulla.
So higher osmolarity means we need more water there.
Exactly, you got it. Higher osmolarity means there are more particles, like sodium or urea, relative to water. So that area is thirstier and pulls water toward it to balance things out. In the kidney's medulla, high osmolarity created by urea and salts during dehydration.
So reabsorbing urea increases osmolarity, which will make us reabsorb even more water.
Boom, you nailed it. Reabsorbing urea in the collecting duct during dehydration boosts the medulla's osmolarity, making it super concentrated and pulling even more water out of the urine through aquaporin 2 channels, helping conserve water and concentrate urine. Want me to tie this back to the countercurrent system or move to another piece of this?
I see. This makes a lot of sense now. Okay, so... Okay.
Sweet. Glad it's clicking.
So we have thirst. To explain us how thirst works.
All right, let's talk thirst and how it fits into fluid balance. Thirst is your body's way of saying, yo, we need more water. It's triggered mainly by two signals, high plasma osmolarity and low effective circulating volume. Osmoreceptors in the hypothalamus detect when blood gets too concentrated, high osmolarity, like above 290 MOSM/SL, shrinking cells and signaling the brain to make you feel thirsty. Baroreceptors in blood vessels, like the carotid sinus, sense low blood volume or pressure, low effective circulating volume, and tell the hypothalamus to kick in thirst too. This thirst signal drives you to drink water, which lowers osmolarity and restores volume. The hypothalamus is the control hub here, just like it is for ADH release, linking thirst to kidney function. Picture it as the house's alarm system. blaring when water's low to get you to refill the tank. Want to connect this to ADH? Or
I
dig
want
into
to
the
understand the differences between osmoreceptors and baroreceptors. It seems like osmoreceptors and baroreceptors have something to do with ADH, but baroreceptors also have to do with ANP and the RAAS and the sympathetic nervous system. And I want to understand why the baroreceptors have all these jobs, whereas osmoreceptors is mainly thirst and ADH. I want to also understand why plasma osmolarity has to do with osmoreceptors. Well, I know that. I can understand why that is. And is effective circulating volume something that has to do with both osmoreceptors and baroreceptors?
Great questions. Let's break it down clearly, like that house analogy, and cover the differences between osmoreceptors and baroreceptors, their roles with ADH, and why baroreceptors have more jobs. Osmoreceptors, found in the hypothalamus, are all about sensing plasma osmolarity, how concentrated the blood is with particles like sodium or urea. When osmolarity rises, say above 290 MOSM/SL from dehydration, these receptors detect cell shrinkage and trigger the hypothalamus to release ADH from the posterior pituitary and stimulate thirst. Their main gig is water balance, so they focus on ADH and thirst to dilute the blood by reabsorbing or drinking water. Baroreceptors, located in blood vessels like the carotid sinus and aortic arch, sense changes in blood pressure and effective circulating volume, how much blood is effectively perfusing tissues. When pressure or volume drops, like in hemorrhage, they signal the hypothalamus to release ADH, but they also activate the renin-angiotensin-aldosterone system, RAAS, to retain sodium and water, and the sympathetic nervous system to raise heart rate and constrict vessels. A for angiotensin, P for pressure regulation. Baroreceptors have these extra jobs because blood pressure affects not just fluid balance, but also circulation and organ perfusion, requiring a broader response. Why the difference?
I'm a bit confused, Broski. Can you tell me again?
No worries. Let's simplify it. And I think you meant grok, not Roski. Haha. Osmoreceptors in the hypothalamus sense high plasma osmolarity, concentrated blood, and trigger ADH release and thirst to conserve or add water, focusing only on water balance. Baroreceptors in blood vessels detect low blood pressure or effective circulating volume, signaling ADH release, but also activating RAAS in the sympathetic nervous system to manage blood pressure and circulation, giving them more roles since pressure impacts the whole body. Effective circulating volume is mainly sensed by baroreceptors, not osmoreceptors, because it's about blood flow, not concentration. Picture osmoreceptors as a water meter reader and baroreceptors as a pressure gauge technician with extra tools for circulation. Clearer now, or want me to hit a specific part again?
I didn't get the answer though about, I mentioned a lot of things, like if the effective circulating volume has to do with both of them and why RAAS is through baroreceptors. I don't even know what the baroreceptors mean, to be honest. What is baro?
Alright, my bad for missing some of your points. Let's hit those directly and clear up baroreceptors in a simple way. Baroreceptors are pressure sensors in blood vessels, like the carotid sinus and aortic arch. Baro comes from Greek for pressure, so they detect changes in blood pressure and effective circulating volume, how much blood is effectively flowing to tissues. Effective circulating volume is sensed mainly by baroreceptors, not osmoreceptors, because it's about blood flow and pressure, not blood concentration. Osmoreceptors focus on plasma osmolarity. When baroreceptors sense low effective circulating volume or pressure, they signal the hypothalamus to release ADH to conserve water. But they also trigger the renin-angiotensin-aldosterone system, RAAS, by prompting the kidneys to release renin, which leads to angiotensin II, raising blood pressure, and aldosterone, retaining sodium and water. RAAS is tied to baroreceptors because low pressure or volume needs a multi-pronged fix. More fluid via ADH and aldosterone, and better circulation via angiotensin II. Osmoreceptors don't mess with RAAS since they're only about water balance, not pressure. Picture baroreceptors as a house's pressure valve crew, calling in ADH, RAAS, and even the sympathetic nervous system to boost heart rate when the pipes, blood vessels, lose pressure, while osmoreceptors are just checking the water's saltiness. Want to zoom in on RAAS or baroreceptor signaling to make it stick?
It's okay. I wanna ask you though about these central vascular sensors. What are these?
All right, let's talk about central vascular sensors. These are sensors located in the central parts of the cardiovascular system, primarily referring to baroreceptors in the carotid sinus and aortic arch, which detect changes in blood pressure and effective circulating volume. They send signals to the brain, particularly the medulla and hypothalamus, to adjust heart rate, vessel tone, ADH release, and trigger RAAS when pressure or volume drops, helping maintain fluid and circulatory balance. Think of them as the house's main pressure gauges, constantly checking the blood flow's force to keep everything running smoothly. Want me to connect this to how they differ from osmoreceptors or dive deeper into their signaling?
Yes, please. I don't know. So they are central vascular. Okay. And we have low pressure and high pressure receptors.
All right, let's clarify central vascular sensors and the low and high pressure receptors. Central vascular sensors, mainly baroreceptors in the carotid sinus and aortic arch, are part of the high pressure receptor system, sensing changes in arterial blood pressure and effective circulating volume. They signal the brainstem and hypothalamus to tweak heart rate, vessel tone, ADH, and RAAS when pressure drops or rises, like a house's pressure gauges keeping blood flow steady. Low pressure receptors, found in the atria, ventricles, and pulmonary veins, monitor venous blood volume and pressure, central venous pressure, triggering ADH release or atrial natriuretic peptide, ANP, to adjust fluid balance when volume is too low or high. Osmoreceptors, in contrast, are in the hypothalamus and only sense plasma osmolarity, driving ADH and thirst for water balance, not pressure. Picture high-pressure baroreceptors as arterial watchdogs, low-pressure receptors as venous volume checkers, and osmoreceptors as blood saltiness detectors. Want to dig into how these signals reach the brain or stick with their roles?
I want to understand a bit about these low pressure receptors and high pressure receptors, and I want to understand a bit about the low pressure ones. Like we had said large veins and cardiac atria and pulmonary vasculature, and then we have high pressure, that's the carotid sinus and aortic arch, and I want to understand why they're grouped this way and what they do. Tell me more about them.
Awesome. Let's dive into low pressure and high pressure receptors and why they're grouped that way, keeping it clear like that house analogy. High pressure receptors are baroreceptors in the carotid sinus, neck, and aortic arch, chest, located in arteries where blood pressure is high and pulsatile. They monitor arterial blood pressure and effective circulating volume, sensing stretch in the vessel walls. When pressure drops, like in dehydration or hemorrhage, they signal the brainstem to boost heart rate, constrict vessels via the sympathetic nervous system, release ADH, and trigger RAAS to raise pressure and volume. If pressure's too high, they slow the heart and relax vessels. Low pressure receptors, found in the cardiac atria, large veins, like the vena cava, and pulmonary vasculature, monitor venous and atrial pressure, which reflects blood volume returning to the heart. These are less about pulsatile pressure and more about stretch from volume. When volume is low, they signal for ADH release to conserve water. When volume is high, like fluid overload, they trigger atrial natriuretic peptide ANP
But
release.
I don't understand why large systemic veins, cardiac atria, and pulmonary vasculature are low pressure receptors, and high pressure receptors are carotid sinus and aortic arch and renal afferent arterioles.
All right, let's clear up why these receptors are grouped as low pressure and high pressure. And I'll correct that the renal afferent arterioles aren't typically high pressure receptors, but rather part of the kidney's local sensing system. High pressure receptors, located in the carotid sinus and aortic arch, are in major arteries where blood pressure is high and pulsatile, around 80 to 120 millimeters mercury in systole, because these areas directly feel the force of the heart's output, making them ideal for monitoring arterial pressure and effective circulating volume. They sense vessel wall stretch and signal the brainstem and hypothalamus to adjust heart rate, vessel tone, ADH, and RAAS when pressure shifts. Low pressure receptors, found in the cardiac atria, large systemic veins, like the vena cava and pulmonary vasculature, are in areas with much lower pressure, 0 to 10 millimeters mercury, because these venous and atrial regions reflect blood volume returning to the heart, not arterial force. They detect stretch from volume changes and trigger ADH for low volume or ANP for high volume to manage fluid balance. The grouping reflects anatomy. High pressure receptors are in strong, elastic arteries handling the heart's pump, while low pressure receptors are in thinner, stretchy veins and atria sensing blood pooling or filling. Picture high pressure receptors as gauges on the house's main water pump, arteries, and low pressure receptors as sensors in the reserve tanks, veins, atria. Want to dig into their signaling or clarify the renal arterioles role?
I want to ask about the renin angiotensin aldosterone system. So, is there something called the principal factor?
All right, let's dive into the renin-angiotensin aldosterone system, RAAS, and address your question about the principal factor. The RAAS is a key player in regulating blood pressure, fluid balance, and effective circulating volume. When blood pressure or effective circulating volume drops, baroreceptors in the carotid sinus and aortic arch, or low pressure receptors in the atria veins.
Can you answer my question directly in a sentence? It was a very simple question.
There's no term called principal factor in the renin-angiotensin aldosterone system, RAAS.
So, okay, can I ask about the juxtaglomerular cells and how they connect to ECV and the RAAS?
Absolutely. Let's break down juxtaglomerular JG cells. They're linked to effective circulating volume, ECV, and the renin-angiotensin aldosterone system, RAAS, in a clear way. JG cells are specialized cells in the walls of the kidney's afferent arterioles, right near the glomerulus, acting like the house's pressure monitors. They sense changes in ECV and blood pressure through three main signals: low blood pressure, detected by stretch in the arterioles; low sodium delivery to the macula densa, a nearby sensor in the distal tubule; and sympathetic nervous system activation, from baroreceptors sensing low ECV. When ECV is low, like in dehydration or hemorrhage, JG cells release renin, kicking off RAAS. Renin converts
I see, so ECV is low and juxtaglomerular cells will activate renin. Interesting.
Yeah, exactly.
And so, do we have a renal baroreceptor and a renal sodium ion sensor?
Yep, you're spot on about the kidneys having specialized sensors. The kidneys have renal baroreceptors located in the walls of the afferent arterioles of the glomerulus, which detect changes in blood pressure within the kidney's blood vessels. When pressure drops, like with low effective circulating volume, these baroreceptors signal juxtaglomerular cells to release renin, starting the RAAS to raise pressure and volume. There's also a renal sodium ion sensor, specifically the macula densa cells in the distal tubule, which monitors sodium chloride levels in the filtrate. Low sodium delivery, indicating low glomerular filtration or volume, triggers the macula densa to signal.
Wait a sec, what's the macula densa? I don't understand. And why are they ideal for their job, and how the name relate to the structure, relate to the function? Same exact question also for the juxtaglomerular, and answer in maximum 3 sentences.
The macula densa is a group of specialized cells in the distal tubule, named for their dense, spot-like appearance. Macula equals spot. Densa equals dense. Ideally positioned to sense sodium chloride levels in the filtrate, signaling juxtaglomerular cells to release renin when sodium is low, to regulate glomerular filtration and blood volume. Juxtaglomerular cells, named for their location next to the glomerulus, juxta equals beside, are in the afferent arterial walls, perfectly suited to detect blood pressure changes via baroreceptors and release renin to activate RAAS when pressure drops. Their names reflect their structural proximity and role in fine-tuning kidney filtration and systemic fluid balance.
One more time.
The macula densa, a dense cluster of cells in the distal tubule. Macula equals spot. Densa equals dense. Senses low sodium chloride in the filtrate, ideally placed to signal juxtaglomerular cells to release renin for blood volume control. Juxtaglomerular cells.
Why are they called macula densa? And why are they called juxtaglomerular?
The macula densa is named for its appearance. Macula means spot, and densa means dense in Latin, because these cells form a compact, spot-like cluster in the distal tubule, where they monitor sodium chloride levels. Juxtaglomerular cells are called so because juxta means beside in Latin, and they're located right next to the glomerulus and the afferent arteriole, perfectly positioned to sense blood pressure and release renin. These names reflect their anatomical structure and location, tying directly to their roles in kidney function.
Okay. Can I ask about high heat exposure and how it affects glomerular filtration rate?
All right, let's dive into how high heat exposure affects glomerular filtration rate, GFR. High heat exposure can lead to dehydration from sweating, which reduces effective circulating volume and blood pressure, signaling the kidneys to conserve water and lower GFR. The drop in blood volume activates baroreceptors and the RAAS, causing afferent arterial constriction via angiotensin II, and reducing the filtration pressure in the glomerulus, thus decreasing GFR. Think of the kidneys as a house slowing the water filter when the main tank's running low to save water. Want me to detail the RAAS role here, or how the body compensates?
Tell me again, I'm a bit confused.
No problem. Let's simplify how high heat exposure affects glomerular filtration rate, GFR. When you're exposed to high heat, you sweat a lot, losing water and dropping your effective circulating volume, which lowers blood pressure. This triggers baroreceptors and the RAAS to constrict the afferent arteriole, reducing blood flow to the glomerulus and lowering GFR to conserve water, like a house turning down the water filter when the tank's low. Want me to focus on one part, like RAAS, or run it again?
I'm a bit confused, bro. I can't lie. I don't get how heat affects glomerular filtration rate.
Yo, no stress, bro. Let's make it super clear. High heat makes you sweat buckets, which lowers your blood volume and pressure. This drop tells your kidneys, via baroreceptors and the RAAS, to tighten the blood vessels, afferent arterioles, going into the glomerulus, slowing down how much blood gets filtered, so the glomerular filtration rate, GFR, decreases to save water. Picture a house with low water pressure closing the filter valve to keep the tank from running dry. Want to zoom in on RAAS or try another angle?
Last time. Yeah, and find another angle maybe too.
All right, bro. Last time, let's nail it in 2. High heat causes sweating, dropping your blood volume and pressure, which makes baroreceptors and RAAS kick in. They constrict the kidney's afferent arteriole, reducing blood flow to the glomerulus, lowering glomerular filtration rate, GFR, to conserve water, like a house throttling the filter when water's scarce.
We're conserving water because we're losing it through sweating.
Exactly. You got it. Sweating from high heat drains your body's water, so the kidneys lower
The
GFR.
constriction of the afferent arteriole is slowing down the glomerular filtration rate.
Spot on. Constricting the afferent arteriole reduces blood flow into the glomerulus, which slows down the glomerular filtration rate, GFR, to help conserve water when you're losing it through sweating. Like turning down the water valve to the house's filter to save the tank. Want to tie this to anything else? Or
I
call it good?
want you to remind me the ANP, the atrial natriuretic peptide, is basically the opposite of aldosterone and ADH, right?
Yo, you're right to connect those dots. Atrial natriuretic peptide, ANP, not ANH.
ANP, I said.
My bad, bro. I misheard ya. Yeah. Atrial natriuretic peptide, ANP, is basically the opposite of aldosterone. ANP, released by the heart's atria, when blood volume is high, makes the kidneys excrete more sodium and water to lower volume and pressure. While aldosterone, triggered by low volume via RAAS, makes the kidneys retain sodium and water to raise volume. Picture ANP as the house's overflow valve opening to drain excess water, and aldosterone as the plug to keep water in when the tank's low. Want to dig deeper into ANP's role or something else?
I want to ask, so we have atrial myocytes. Why are the atrial myocytes in the heart the ideal ones to synthesize and store ANP? Why not the ventricles? Why not the blood vessel? Yeah.
Great question about why atrial myocytes are the go-to for atrial natriuretic peptide, ANP. Atrial myocytes, the muscle cells in the heart's atria, are ideal for synthesizing and storing ANP because the atria are super sensitive to stretch from increased blood volume or pressure, which happens when blood returns to the heart. When the atria stretch, like in fluid overload.
So when they stretch, then, man, this is the perfect mechanism. That's so clever.
Yo, right? It's like the body's got this genius setup. When the atria stretch from too much blood volume, atrial myocytes release ANP like a perfectly timed alarm, telling the kidneys to dump sodium and water to ease the load.
What is the application and significance of mathematics being a discovery or an invention?
Whoa, that's a sharp pivot from kidneys to a deep philosophical question. Whether mathematics is a discovery or an invention has big implications. If it's a discovery, Math exists independently in the universe like laws of physics, and we're just uncovering truths that govern reality, meaning math is universal and applies to everything from kidney filtration rates to planetary orbits. If it's an invention, humans created math as a tool to describe patterns, so its significance lies in our ability to model and predict stuff.
Yeah,
like fluid.
and I guess if it's an discovery, does it okay? And what are the applications and conclusions? Like, what are the inferences we can gain in metaphysics in regard to if materialism or idealism is correct?
All right, let's dive into the metaphysical implications of whether mathematics is a discovery or an invention, and how it ties to materialism versus idealism. If mathematics is a discovery, it suggests math exists as an objective, universal truth in the universe, leaning toward materialism, a view where reality is grounded in physical laws and structures, like Platonic forms, implying the universe has an inherent mathematical order independent of human minds, e.g., kidney filtration follows mathematical ratios. If math is an invention, it supports idealism, where math is a human construct, a mental framework we impose on reality to make sense of it, meaning our perception shapes truths about fluid balance or physics. The inference: discovery favors a materialist view of a mind-independent reality, while invention aligns with idealism, emphasizing mind-dependent constructs, affecting how we understand the nature of existence itself. Want to explore how this impacts science, or stick with metaphysics?
No, this is great. Okay. Sorry, guys. So how does so more sodium when we have A and P reaches the macula densa, but why? Explain to me again this macula densa, and how will renin be reduced because of it?
No worries. Let's get back to the kidneys and clear up how A and P, the macula densa, and renin release connect. The macula densa is a cluster of cells in the distal tubule, right where it touches the glomerulus, perfectly placed to sense sodium chloride, NaCl, levels in the filtrate. When atrial natriuretic peptide, ANP, is released due to high blood volume, it makes the kidneys excrete more sodium and water by dilating the afferent arteriole and increasing glomerular filtration rate, GFR, which sends more NaCl to the distal tubule. The macula densa detects this high NaCl, signaling the juxtaglomerular cells to reduce renin release.
Where exactly is the macula densa?
The macula densa is a group of specialized cells located in the wall of the distal convoluted tubule, right at the point where it passes close to the glomerulus, near the afferent and efferent arterioles in the kidney's nephron.
One more time. Where is it in a sentence?
The macula densa is a cluster of cells in the distal convoluted tubule's wall, positioned where it contacts the glomerulus, near the afferent and
And the job is to release renin.
Actually, the macula densa itself doesn't release
It's the
renin.
juxtaglomerular cells.
Yep, exactly. You got it. The juxtaglomerular cells, located in the walls of the afferent arteriole next to the glomerulus, are the ones that release renin, while the macula densa, nearby in the distal tubule, senses sodium chloride levels and signals the juxtaglomerular cells to adjust renin release. When the macula densa detects high NaCl, like with ANP increasing GFR, it tells the juxtaglomerular cells to cut back on renin to reduce RAAS and sodium retention. Want to tie this back to ANP or dive into another kidney detail?
Fuck. What do the macula densa... Guys, I'm so sorry. I just can't figure out what the macula densa do. It reminds me, Lex Friedman was talking to this IT guy, and he was saying to him, like, I repeated my homework 20 times. I was reading it, again and again and again and again and again. I didn't understand it. This is how I feel, but yeah. Anyway, tell me. In a sentence. Let's not make it complicated.
The macula densa is a spot in the kidney's distal tubule that senses sodium chloride levels in the urine and signals the nearby juxtaglomerular cells to tweak renin release, helping control blood pressure and fluid balance.
One more time.
The macula densa, a group of cells in fracasso. Come on, why are you saying words like distal tubule? Dude, it's already complicated as it is. Just say it's simple. Simpler in a sentence.
Shut up. Sorry, guys. I think Grok does this thing sometimes. He gets confused and he repeats what I say. Anyway, dude. Okay. Can you tell me again, in a sentence, what macula densa does and how the name relates to the structure and function? And then we'll continue.
All right, dude. My bad. Let's keep it super simple. The macula densa is a tiny spot of cells in the kidney tube near the glomerulus. Named dense spot, macula means spot, densa means dense, because it looks compact, and its job is to check sodium levels in the urine and tell nearby cells to adjust renin for blood pressure control. Want me to hit how this ties to ANP?
That's okay. And why is posterior pituitary, I think, is the... I don't remember actually. What's released in the posterior pituitary?
The posterior pituitary releases two hormones, antidiuretic hormone, ADH, or vasopressin, and oxytocin. ADH is the one we've been talking about, controlling water reabsorption in the kidneys to manage fluid balance, while oxytocin is mainly involved in childbirth and lactation. Want me to focus on ADH's role from the posterior
Why
pituitary?
we want oxytocin in birth? Is it to relax the mommy?
Good question. Oxytocin, released from the posterior pituitary, isn't exactly to relax the mom, but to help with childbirth by triggering uterine contractions during labor, making them stronger and more coordinated.
How does it make contractions stronger?
Oxytocin makes contractions stronger by binding to receptors on uterine smooth muscle cells, triggering a signaling cascade that increases calcium release inside the cells, which amps up muscle contractions in the uterus during labor. Think of it like oxytocin turning up the volume on the uterus's contraction machinery to push the baby out. Want me to dive into the signaling details or how it affects milk ejection too?
I don't get it. If you could tell me again what the reason.
All right, let's break down the signaling cascade for oxytocin in a simple way. When oxytocin binds to its receptors on uterine smooth muscle cells, it kicks off a signaling cascade, which is like a chain reaction. The receptor activates proteins inside the cell, boosting calcium release from storage sites, and this calcium makes the muscle fibers contract harder and more often.
Can I ask, the angiotensin 2, so its actions increase ECV, effective volume or whatever it is called, but at the same time, why would vasoconstriction occur? Wouldn't that slow things down?
Great question about angiotensin 2 and its role in effective circulating volume, ECV. Angiotensin 2, part of the RAAS, increases ECV by promoting vasoconstriction and stimulating aldosterone release, which makes the kidneys retain sodium and water, boosting blood volume. Vasoconstriction, narrowing blood vessels, might seem like it slows blood flow, but it actually raises blood pressure by increasing resistance, which helps maintain perfusion to vital organs when ECV is low, like in dehydration or hemorrhage. This increases blood pressure to maintain perfusion and signals the kidneys.
I know that it increases blood pressure. I'm just saying, doesn't increased blood pressure mean that we will have a slower effective volume.
I hear you, and that's a sharp observation. You're right that vasoconstriction from angiotensin II increases blood pressure, but it doesn't necessarily slow down effective circulating volume, ECV. Instead, it helps maintain or even boost ECV by ensuring blood is still pushed effectively to tissues despite low volume. Here's why. Vasoconstriction narrows blood vessels, raising pressure to keep blood flowing to vital organs, like the brain and kidneys, while angiotensin II also triggers aldosterone and ADH to retain sodium and water, directly increasing blood volume and thus ECV.
Okay, so question. By itself, independently of everything else, would a vasoconstriction increase or decrease effective circulating volume? Answer in 3 words.
Decrease effective circulating volume.
But basically, because of other things, it's not as big as an effect. So overall, we have an increase. Answer yes or no.
Yes.
Booyakasha. Okay. And how can angiotensin II cause renal cell hypertrophy? Is this yeah. And how does this lead to more protein synthesis of sodium ion transporters and channels?
How? We akasha indeed. Angiotensin II causes renal cell hypertrophy, particularly in proximal tubule cells, by binding to AT1 receptors, activating signaling pathways like MATPAC and mTOR, which ramp up protein synthesis and cell growth, leading to larger cells. This hypertrophy increases the production of sodium ion transporters and channels, like the sodium-potassium ATPase and sodium-hydrogen exchanger, because the pathways boost gene expression for these proteins, enhancing sodium reabsorption to raise blood volume. Think of angiotensin II as a gym coach for kidney cells, making them bulk up and pack in more sodium-handling gear. Want to dive deeper into the pathways or connect this to RAAS?
Okay. I don't get why angiotensin II. You have to answer to me again in a sentence or two why angiotensin II causes renal cell hypertrophy, and also why protein synthesis will occur as a result, and we will have sodium transporters and channels.
All right, let's tackle angiotensin II and renal cell hypertrophy, plus the MPAC pathway in a clear, concise way. Angiotensin II causes renal cell hypertrophy by binding to AT1 receptors on proximal tubule cells, triggering the MPAC pathway, mitogen-activated protein kinase pathway, which signals cells to grow larger and boosts protein synthesis of sodium ion transporters and channels, like the sodium-potassium ATPase. The MPAC pathway is a signaling cascade that, when activated by angiotensin II, turns on genes for cell growth and protein.
No. Answer the question I asked in a sentence.
Angiotensin II causes renal cell hypertrophy by activating the MPAC pathway via AT1 receptors, promoting cell growth and increasing protein synthesis of sodium ion transporters and channels in proximal tubule cells.
Okay, so we'll have decrease in the ECV, baroreceptors, renal baroreceptors, and renal sodium ion sensors feel it. So one thing that's going to happen is we have activation of the RAAS, angiotensin and aldosterone will increase, and we will have reabsorption. Okay, I understand that. Then we might have peripheral baroreceptors detecting it, and the peripheral ones will act in the hypothalamus in the brain, and then the sympathetic nervous system will be activated. But I am a bit confused why the peripheral ones will have to do with this hypothalamus and the sympathetic nervous system. and not other types of receptors.
All right, let's clear up the confusion about why peripheral baroreceptors specifically tie to the hypothalamus and sympathetic nervous system. When effective circulating volume, ECV, drops, peripheral baroreceptors, located in the carotid sinus and aortic arch, high pressure sensors, detect the fall in arterial blood pressure and send signals via nerves to the brainstem, which then relays the info to the hypothalamus. The hypothalamus responds by activating the sympathetic nervous system to increase heart rate and constrict blood vessels to raise pressure, and also triggers ADH release from the posterior pituitary to conserve water, both boosting ECV. Peripheral baroreceptors are uniquely wired to the hypothalamus and sympathetic system because their job is to quickly sense arterial pressure changes and coordinate rapid, body-wide responses to stabilize circulation. Unlike osmoreceptors, which focus on osmolarity and ADH thirst, or low-pressure receptors,
Okay,
which...
this was the episode for today, guys. I hope you enjoyed it. Peace.